Hello again, everybody. This is part 2 of week 1 of remote learning for honors chemistry. Again, I was asked to show my face in these videos, but here's my picture of what I hope to be doing during part of these working remotely. That's me going hiking. So anyway, there you go. There's my face. All right, so here's I'm gonna do this video with my little document camera. The notes I've posted in materials. This is part 2. This replaces pages 10 and 11 of the notes. I will post the slides that go with this if that's easier for you to watch the slides instead of watching the video. I don't care which one you do. All right, so Hess's law is another way to find the heat of reaction. If you add 2 or more thermochemical equations to give a final equation, you can also add the heats of reaction to give a final heat of reaction. So you're taking 2 sort of mini equations and putting them together to find a goal equation. That's what I call it. So on this one we have 2 of these mini equations, and we're using those to solve for the change in enthalpy for this goal equation. So this is the goal that we're trying to reach. What I do is I look at my mini equations and I just look for the very first compound on the list, and then I rewrite it. And I also include the delta H. All right, so when we look at the next one in our goal equation, it's already there. Okay, and then on the product side, that already matches. The last compound here, we can see that we want this to be a gas instead of liquid. So we're going to have to be able to cancel this one out. So we're going to use the second equation to cancel out this 2 moles of water that's liquid. So essentially what's happening in this is we have a combustion reaction. We typically write the water as liquid, but in reality the heat that's produced in this combustion reaction is going to vaporize this liquid water into gas. Okay, so we're going to take our second equation. Okay, we can see that the liquid water is on the right in the first equation and on the left in the second equation. So those are going to cancel out. We can see here that this is the heat of vaporization, by the way. Now, in our goal equation, we're going to need 2 of these gaseous water. So we're going to put a 2 here. Now, if we want this to be 2 moles of water, we're going to need to start with 2 moles of water. We're essentially doubling all of this. That's also going to double our delta H. So we're going to multiply our delta H by 2 as well. By the way, there are probably 10,000 other videos on this topic, so just Google or go into YouTube, Hess's Law, and you'll see a ton of different practice problems for this. Okay, so now what we do is we're going to add our 2 reactions together. Now some of this cancels out. This cancels out, and this cancels out. And if we put all of this together again, I like to line up the arrows so we can see what's on the left and right. Okay, now our equation that we put together matches our goal equation. Okay, that means that we can actually add these 2 heats of reaction together to get a final heat of reaction. So just type this in your calculator, negative 890 plus 40.7 times 2. If you do that, you should get negative 808.6 kilojoules per mole. Okay, so that's your answer. So all of that other work was just to get this answer out of the end of this. All right, so I'd like you to try these other 2 problems. Give those a try. I will post the answers online. If you did it right, let me find my answers, hold on. If you did it right, this one you should get negative 595 kilojoules per mole. And this other one you should get negative 296.1 kilojoules. Okay, here's the back. All right, the standard heat of formation. Okay, now this is another type of heat of reaction. The standard here is under standard conditions, which is 25 Celsius and 1 atmosphere of pressure. You will look at that further if you go on and take AP Chemistry. Okay, but this is called standard heat of formation, okay, which is the change in enthalpy okay, and remember this is heat content at constant pressure that accompanies the formation of 1 mole of a compound from its elements. Okay. The delta H standard of formation is 0 for all elements. So for example, if you're taking O2 and making O2, like the delta H of that obviously is going to be, the delta H of that is going to be 0 kilojoules because nothing's really happened. So, you know, some sample data here we've got, and it's always set for 1 mole. So we have 1 mole of nitrogen monoxide. So that's why we have these funny little half coefficients there. But it's just so that this is per 1 mole. But that's the heat of formation for each of these. So these happen to be endothermic. Sometimes they're exothermic. Okay, so if we want to use these equations like we did for Hess's law, we can do that. We would flip around some of these equations just like we did the last time. This is our goal equation. So we can see that the NO is on the reactant side. So for the first equation, we want to flip that around. I probably should have mentioned in the earlier part of this video that if you flip the equation over, you're going to have to change the delta H to opposite, negative 90.37 instead of positive 90.37, because if it's the opposite reaction, it's the opposite change in heat. Now for the 2 here, we're going to need to multiply everything here by 2, including the delta H. All right. For the second part, this is on the other side, so we don't have to change the direction. Oh shoot. I have to do this perfect, kids, because I only have 1 copy of this. All right, let's see. We're going to need 2 of those, so multiply everything by 2. Okay, we're going to add these together. Cancel this, cancel this. This is 1 oxygen, so that cancels, but it only cancels out 1 of these 2 oxygens. So then what we have left is 2NO plus O2 plus 2NO2, so that matches our goal equation. When you add up these heats of reaction, you end up with negative 113.04 kilojoules per mole. Okay, so that is this delta H standard for this reaction. Okay, I'll show you a shortcut because that was a lot of work, right? Okay, so the change in enthalpy calculated using the standard heats of formation. Okay, so there's a faster way to do this. We take the sum of the delta H standard for the products minus the sum of the delta H standard of formation of the reactants. This is a formula that's used a lot in AP chemistry. It's really easy. You just take the heats of formation of the products minus the heats of formation of the reactants, okay, and you'll see that it's actually the same exact thing that we did over here. Okay, so then what we do is, it's helpful sometimes to write this out. It's like extra work, but I think in the long run it's easier. So we want to take our products, which was 2 of the NO2s, minus the reactants, and we do need to include the coefficients. So we have 2 of the NOs. And you'll recall that oxygen is 0. The heat of formation for oxygen is 0. But I'm just going to write that for fun. Okay, so for the NO2, back in our little data table here, the NO2 was 33.85. Now, really the only trick to this, other than just plugging numbers in, is to make sure that you're keeping your negatives and positives aligned. So this is negative here. If this happened to be negative, those 2 negatives would cancel out. Okay, so just, I would say type everything in your calculator and let your calculator crunch the number for you. If we look at our earlier problem, you can see that we're doing the exact same thing we did before with Hess's law. Okay, so you're going to get the same answer. Okay, but the second version is much faster. So if you have the heats of formation, you just do products minus reactants instead of doing all that Hess's law work that we did there. Okay, so I'd like you to try these other problems that are on here. So pause the video and actually do these. For F, you're going to have to balance the equation first. But you should get, in the end, negative 566.0 kilojoules per mole. Now, if you think that I've done these problems not correctly or crunched the number wrong, please email me. All right, let's see. All right, so we're almost done. You have a couple more problems to try here. If you did them right, you should get negative 6339.6 kilojoules per mole, and you should get 492.7 kilojoules per mole. All right, so your quiz, your group quiz that's going to be due on Friday is not on this material. I'll quiz you on this material next week. All right, good luck with everything.